Hi guys, so in this video I'm going to explain binary search to you. So let's start with a few terminologies. The first one is the objective. So whenever we are solving a question related to binary search, you should try and find out what the objective function is. So basically the objective is given a monotonic function. This is very important. Given a monotonic function f of x, we want to find an x such that f of x equals to some constant c. So what this actually says is, let's suppose we have a graph and this is some monotonic function fx, and we have been given a value c. So this is a straight line parallel to the x-axis and this value is c. So what we want to do is we want to find this x that is corresponding to this value c. This is our objective function. So whenever we are given a question, if that's related to binary search, then it's always possible to reduce the question into this objective. Okay, let's now try and understand what the search space is. The search space it's a region where our answer is going to lie. Let's suppose this function fx is a bounded function and is bounded between x2, x1 and x2. This value is x1 and this is x2. So initially the answer is going to lie between x1 and x2, any integer point, any point between x1 and x2. In the next iteration, what we are going to do is we try to reduce the search space in such a way that we narrow my answer down to x, the value x. So this is our aim, what we want to do in binary search. Now, how we do this is going to be defined by our predicate. So predicate is nothing but a Boolean function. I hope you know what a Boolean function is. It's any function that returns value true or false, and on the basis of that we are going to reduce our search space. So binary search, you can say that it's essentially a hit and trial method. Okay, so what we do initially is we take x1 and x2 and we find the mid of this. So we say that let's try to evaluate our predicate. Let's try to evaluate our function at this point, at the midpoint. So what we find is that the function value is not equal to c. Okay, let's try to make this more clear. It's going to be like this, and the value of this is somewhere down below, right? So what we can say that since this function is monotonic, we can move towards the right. So what we do is we move towards the right, and after that the search space becomes x. So let's say this is xa. So the search space now becomes xa till x2. Now we are going to try and find the x value, the answer value within this region. All the region below xa is going to be useless for us because we know that this is a monotonic function. So what our Boolean function can be is, if the value of fx is greater than c, if it's less than C, then I'm going to return, let's say, false. And if it's fx greater than C, greater than or equal to C, I return a true. So essentially what this predicate function is doing, it's giving us signal where we should move. We are going to move in only one direction, either right or the left. If it returns false, I'm going to indicate to my pointer that move to this value xa. So initially my low pointer was at x1 and my high pointer was at x2, and my xa was the midpoint. So what I do is, when I get an indicator that the function is less than C, I'm going to move my low pointer to my mid. So my low becomes xa and my high remains x2. So this indicates that my search space has been reduced to xa till x2. If suppose then in the next iteration I find some value xb lying over here, so I calculated the mid again and I found that this value is going to give me a function value greater than or equal to C. So since this is greater than or equal to C, what I do is, it is going to return true. The predicate function is going to return true, and hence I get the signal that I should move my high pointer to the mid. So initially it was low was xa, high was x2, and my mid, that is xb, was equal to, this was the mid. So the new high, the new low, after updating the values of low and high, I get low equals to xa and high equals xb. So my search space has been reduced again from xa till xb. So as you can see that now my low is xa and high is xb. So my search space has again been reduced, and so in this way, in this manner, we are going to always hit and try on the mid and see what and check out what the signal we are receiving from the predicate function, and accordingly we can always exchange these signals. Like fx less than C can return true if we want. It's basically a signal that we want from the predicate function, so that we can tell our pointers to move accordingly and reduce the search space. So after a while it's definitely going to converge to this point and we are going to get our answer. So in general, the questions that we see in the interviews or any competitive programming sites, they do not give a direct function that you already know to binary search upon. So you have to analyze the question first, and you have to identify the function that is associated with that question, and accordingly do the binary search. So whenever we look at the predicate function, it's always going to be of one of these forms. It's either going to be false, 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 and then true, 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 something like that, or it can be true, 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 and false, 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 false. So it's either one of these forms. It's basically this type of signal that you're associating with your predicate. You can do any of these things, and the objective after finding the predicate function becomes to find this intersection. So generally what we want to find is either the first false value, or either the last false value or the first true value in this kind, or the last true and the first false in this kind. Let's talk about only this one. Let's forget about this. So, and that basically depends on my predicate function. So what this says is that fx greater than equal to c is going to return the true value. So this particular true value that we are seeing is essentially going to be associated with our answer, not this one. If, however, it was the reverse case and I remove this and plug it over here, so this becomes the last false value is going to actually decide my answer. Okay, so let's clarify this once again. This false, 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 true, 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 true. It's basically this area. So this is my answer, and everything on the left is going to be the false, is going to return a false value. Since I know that this is a monotonic function, fx is going to be less than c. And this, all this value is going to return a value greater than c, and that's why this is ffff and then tttt. Okay, now let's try and solve the simplest example that you can find. Given a sorted array, we have a sorted array and that's increasing, and we have indices of, let's say, 0, 1, 2, 3, 4, 5, and we want to and we have the values in the sorted array as, which is basically ai, and this is going to be, let's say this is 5, 7, 8, 15, 30. Okay, so let's try and reduce this question of finding the I. We want to basically find the I where a of I equals to, let's say, 15. So what we actually want to do in this kind of question is we first want to reduce it into the objective of the type that I showed you above. So we want to find the function. In this case, the function is simple to identify because we are trying to find I where ai equals 15. So it's we can see that this is the search space we are going to associate with, and our answer is going to lie in this. So it's basically some mapping from I till a of I, right? So f is going to be a mapping from I till a of I. We want to find this I where a of I equals 15. I know that this isn't going to be a continuous function, but it needn't be the case. The same logic applies everywhere. This is a monotonic function, and that's enough to do a binary search on this. Okay, so after finding the function, what we should try and do is find the predicate of this function. So in this case, the predicate is similar to the above one that I showed you earlier. So it's going to be if f of x less than 15, then I can return a false value, and when f of I is greater than or equal to 15, then I return a true value. So basically the search space associated with this predicate, it's going to be something like this. So we can see that in this search space, we are going to find the last true value that, no, the first true value that appears in this search space, and that's going to give our answer. All right, so now let's look at the pseudocode so that you can be comfortable with any kind of question that is given and you are able to solve it without falling into the edge case traps, and you don't have to get stuck in an infinite loop, which happens to many of us in binary search when we are trying to learn it initially. So okay, let's consider this kind of search space. The pseudocode that I'm going to tell you is basically for this, and you can adjust it for TTTTFFF. That's something else. So the first case that I'm going to show you is for the first true value. I want to find the first first element that gives me the predicate of true, the first true value. So in this case, my loop will be like this: while low less than high. Let's say we have already set our lows and highs over here. Let's say these are defined over here, and I run this loop till low less than high, and I find the mid value, and let's say this is low plus high over 2. And what I do is, if my predicate value, this is a predicate function, and I feed a mid value over here, that is, I give some mid value over here, and if suppose, let's say it returns a false, what I'm going to do is I'm going to move my low till mid plus 1. Why I have done this plus 1? Okay, so this is a question that many people ask. The answer is that I'm not interested in the false values. I'm only interested in the first true value, and the low is always going to be lurking around in the false value region. So whenever I find the false, I'm just going to update it to the next position. So if at the end I have something like this, then my pointer is comfortable in moving over here, and I'm able to break the loop. So this doesn't get stuck in an infinite loop ever. Along with that, if my mid value gets the value true from the predicate function, then I'm going to make my high equals mid. Okay, here I have not done the plus 1 because I am interested in the true values. All right. Another question that many people ask is, when should the mid be low plus high over 2, and when it should be low plus high plus 1 over 2? So to counter understand this kind of understand the methodology when we should use that, let's say our search space get reduced to ft. So now my low is over here and high is over here. So let's say low equals 3 and high equals 4, and mid value is going to become 3 plus 4 over 2, which is equal to 3. This gives the value 3. That is, it points to the low value again. So if my predicate value becomes false, I'm going to do an updation and go to mid plus 1. Now if it so happened that my mid value was low plus high plus 1 over 2, in that case my the mid value would have become 4, and in that case my predicate would have returned true and high would become mid. So basically the high would have gotten stuck over here. So that's why I'm not going to use this. This kind of updation of mid is used only when I'm trying to move the high value to the left when this kind of situation occurs of FNT. So now I think you'll be able to understand the second case. The second case is simple. We want to find the last false value. So in this case, the whole thing is going to be same except for a few changes. So Let's copy paste this. So it's going to be the same, except in here I'm going to place a +1, and the low value over here is going to update only till mid, because we are interested in the last false value. So if my predicate is returning a false, I don't need to move it to the next position, because we might be interested in that particular mid, and the high value is going to update over here till mid -1. So in the situation like this, I'm always going to pick up my mid is always going to be this, and when this is the mid, I'm going to get the true value, so I'm going to update my high till mid -1. So ultimately my aim should be to make low and high equal, so that I'm able to break out of the loop. So in this case also, I'm able to break out of the loop. I think now you'll be able to comfortably solve the question when where the search space is of the type TTTTFFFF. Another point that I must mention is about the mid value. So when we are trying to update the mid value, let's say I'm trying to update it to low plus high by 2, I shouldn't do it like this. Let's say the value low plus high overflows the maximum limit of the integer variable. So let's say it's even bigger than the long. So if say low is the maximum value of long minus 10, and high is the long maximum, so then definitely when we are trying to calculate mid equals to low plus high over 2, it's going to first evaluate the numerator, and after that it's going to divide it by 2. So in that case, definitely an overflow will happen, and we are going to end up with a negative mid value. So what we should always do in such a kind of case is we should update mid to low plus high minus low over 2. And when we are dealing with the case with the second case, we should update our mid to low plus high minus low plus 1 over 2. These things should be remembered, because it's very important you don't fall into such traps. Okay. All right. So if you're not comfortable with all the +1s and -1s in these two steps, where we are doing the +1, where we are doing the -1, with the mids and the lows and the highs, then I suggest that you follow another method, and this involves a little bit of trick, so that you're able to do the binary search without thinking of any edge cases that is going to occur. So what I do here is that I run the loop until high minus low is greater than 3. And in this loop, the mid is going to be updated without the +1. So it's going to be high minus low, low plus high minus low upon 2. And if I have P of mid equal to false, then I just update it to low equals mid, else I do a high equals to mid. I don't care about the +1s or -1s. Okay, let me say this again. The search space is the same. It's FFFF, TTTT. And after that, after this loop is over, what I do is, since I'm left with a search space where high minus low is less than equal to 3, so it's, let's say the search space that I'm left with is FFT. So low is over here, high is over here. and high minus low is 3. So in that case, I do a linear search. If suppose I want to find the last false, what I do is I traverse from the right side and I find the first occurrence of false while traversing like this. So what I do is I run a for loop, and in the reverse manner, that is high to low. If P of mid, P of so I is basically going from high to low. If P of I is equal to false, then I can rest assured that this is the last false in this search space, and basically the first occurrence of false that I found, and my answer is going to be this I. Okay. Similarly, if I want to find the first true, I just traverse from in the forward direction and check the first occurrence of true that I find. So it's basically not going to be reverse. I just use it from I low till high, and the first occurrence of true will give me the answer. Okay, this was the method of not of basically using binary search, and after that small linear search that is not going to compromise the time complexity. Okay, let's now solve a bit difficult question on binary search, and that I'm taking from the Codeforces site. It's the Coffee and Coursework hard version, and we are going to solve it using binary search. The question says that Polycarp has n cups of coffee and each contains AI amount of caffeine. Okay, now Polycarp has to finish writing K papers over several days. Another property of, okay, so now Polycarp needs caffeine which gives him energy to write the paper. So for any day D, for any arbitrary day D, let's say he drinks, okay, these are M papers. Let's say he drinks K cups of coffee, and let's say these are AI1, AI2 till AIK. Then the total amount of energy, basically the total number of papers that he can write over the day, is going to be AI1 plus AI2, maximum of AI1, 0 plus maximum of 0, AI2 minus 1 plus it goes on till maximum of AIK minus K minus 1. This is basically he drinks the coffee in a particular order. The order is not given to us. We can have him drink in any order. All right. So the second term basically represents the ordering. So essentially each cup is going to give him maximum 0, Aij minus j minus 1 amount of coffee energy. So you can write these many papers. Now the question says that he has to write M papers over several days. So if he starts, let's say he has 2, 5, 2, 7 and 5. These are the coffees that he drinks on some day D. Okay, so the amount of energy that he gains is 2 minus 2 plus 7 minus 1 plus 5 minus 2. It's basically 11. Okay. Now finally, coming to the end of the question, it asks us to find the minimum number of days over which Polycarp can finish all the work. Finish reading or working on all M papers. We want to find the minimum number of days. So if suppose I had only 3 cups of coffee and they were 2, 7 and 5. So what's the minimum number of days required to finish 12 cups of coffee, 12 papers? So what I would actually do is I wouldn't allow him to drink all the cups of coffee in the first day itself, because the maximum I can get from drinking all these cups on a single day is 11. So it's rather better to use 7 plus 5 plus 2 minus 1, and that's going to yield. So this is being drunk on the first day and this on the second day. So it's basically 13. So he can finish 13 papers. So 2 days are enough to finish, but 1 is not sufficient. So essentially, what I want is that if I'm given X number of days, if I have X days, how many papers can Polycarp finish? Maximum number of papers he can finish. If I have that, then it's simple. I can just check the day on which I can just find the minimum number of days that is required to finish all this work. It's because the mapping, it's basically days to maximum papers. This mapping is monotonic. The reason is that if suppose I have 5 days in 5 days suppose I can work on 10 papers, then it's sure that if I have 6 days, then I can complete greater than or equal to 10 papers, right? So that's what my function, the objective should be, to do a binary search on this function and find the answer. But how can I find a function that gives me days to maximum papers mapping? So what I can do is I can rearrange the array. Let's take an example over here. So if I take this example, this is M and this is N, and these are the AI values. So what I do is I sort this array, so it becomes 4, 4, 3, 2, 2 and 1, 1. So let's suppose I have been given 3 days. Let's suppose that the value that I predict is going to be 3 days. So essentially it's like this. This is some answer that I want, and I'm making a prediction that 3 days is going to be enough. So let's say I have this at 3 over here. So how many number of papers can I finish in 3 days? It's just simply hidden trial. So in 3 days, how many papers can I finish? So it will be maximum number of papers. What I'll do is I'll divide it into 3 groups, and for the maximum ones I just place it over here. So I traverse it cyclically. I traverse this array in a cyclic manner, and after every 3 blocks that I cover, I start subtracting -1. So start subtracting 1. So it's 4, 4, then 3, and so in this amount of time I'm able to complete 11 papers. Let's say this value is 17. Okay, so or let it be 15. Okay, so m equals 15 for this case. So what will happen is after 4, 4 and 3, it's 11 till now. After that I come to 2, and what I can do now, since I have only 3 days, this is a constrained optimization. So I have 3 days and I want to maximize the number of papers that I read. So I take this cup and I use it over here. So it's +2 -1, whereas the next day it's going to be -1. And after that again I take this cup, it becomes 2 -1 plus 1 -1, and plus maximum of 0, 1 -2, which becomes 0. So the maximum number of papers that I can read within 3 days, it's going to be 4 plus 4 plus 3 plus 1 plus 1 plus 0 plus 0. It's going to be 8 plus 11, 13. These are 13 papers. So what this conveys us that 3 days are not sufficient to read 15 papers. So what I'm going to do, so it's not over here, it's the 3 is over here, and the answer is going to lie somewhere over here. So I make this my low, and the high value is going to be somewhere over here, that I'm going to take any arbitrarily large value, or I just take the maximum number of days that I have for reading. So it's going to be n, obviously, because anything more than n number of days, it's just going to be useless. So because we are essentially over the n days, we are utilizing all the capacity of the caffeine that we have. So high is going to be n over here till now, and after that we do low plus high over 2. I again find the d that over the days, I again find the number of days over which I want to find the maximum number of papers, and again try to find the answer. So this was the function as the maximum number of papers. So now we have covered making the function for this algorithm, and let's move on to make the predicate. So my hidden trial value is the number of days, right? And the output it gives is the number of papers. So if this value, the number of papers that I received for d days is greater than equal to k, let's say I return a true for that. Otherwise, I'm going to return a false. Okay, so this is going to return a false since m equals 15 and this is 13. So 13 is less than 15, so I return a false. So my predicate is going to be pages of d greater than equal to k returns a true, less than k returns a false. And so I get a search space like this, and I choose the first true value that I obtain. So this is exactly like the case 1, and we can use that code to find the answer. Okay, let's move on to the coding portion. Okay, so let's come to the code for this question, and what I have over here is a template that you don't need to worry about at all. After this is the code for this question that you actually have to understand. So in this question, I have two inputs, n and k. So the k is, I've taken k to be the number of papers that has to be read. So I input these, and I also take input in a vector, basically an array, just like this. And I sort the vector and reverse it. So I rearrange the caffeine amounts so that it's easy for me to code the function value. Okay, and initially the search space is from 1 till n, and what I do over here is if the sum of all the elements in the vector is less than k, then definitely I'm not going to be able to read the number of papers that has been given. So what I do is I jump over here and print a -1, which is according to the question, it's given in the question. Now I start my binary search. It's exactly the same as I showed you in the case 1 for finding the first true value in the search space. So this is that, and this is the predicate function, and this is essentially the function that is encapsulated inside this. So what I can do is I can make another function as well for more clarity, and that can be written over here. And let's return f of comma b whether this is greater than or equal to k. Okay, it returns true if the function value is greater than or equal to 2, and this returns the sum. So essentially what's happening is for each of the elements, so it's basically this algorithm that I showed you over here. This algorithm. So I sorted this in the reverse order, and I tried to, and I have the number of days fixed, which is basically the mid in the question, mid in my code, and I'm going in a cyclic manner. Basically, I'm traversing the array and taking this to count the number of cycles. So initially the cycle number is 0, and I'm not going to reduce anything from that. After each cycle, it's, so I'm increasing the value of c, and after each cycle, c over mid is going to be the number of cycles, basically the cycle number with starting from 0. So initially the cycle number is 0, and after one cycle, the number of days, basically if after 3 elements, when I encounter this, the c over mid value is going to give me 1, and after another cycle it's going to give me 2, and so on. And this works like this, and it calculates the maximum value. The sum is basically accumulating all the values that I showed you over here. So yeah, so 4 plus 3, then 2 minus 1, then 2 minus 1, then 1 minus 1, and then 0. So it's accumulating all these values. So this essentially is the function that finds that maps the number of days that we have to the maximum number of papers that can be read in mid number of days. And this returns the sum, and I check in the predicate whether it's greater than or equal to k. And the final answer is definitely going to be stored in low and high as well, because I'm breaking only when low is equal to high. So this is the end of the code, and it probably works. I'm not sure. I changed a few things, so might happen. Yeah, it works. So I'll share the code with you guys, and That's it. Thanks.